Welcome to Unit 5, Day 5 notes, solving exponential equations. So like we did the other day with log equations, there's two types of exponential equations. We'll call them type 1 and type 2. Type 1 is when you have the same base. It might be obvious that it's the same base, or you might have to do a little thinking to make them be the same base. So step 1 is to change each base so that they're the same. And you have to use a smaller number. Once the bases are the same, you set the exponents equal to each other. So let's look at this first example. 16 is 2 to the 4th power. 1/8 is 2 to the -3 power. So all I did was change the left side and the right side to have the same base, and I knew that that base was 2. Now that the bases equal each other, I can set the exponents equal. Let's take a quick look at what the exponent is. Because it's power to another power, this is one of the rules of exponents, I multiply those two powers. Same on the right hand side. Okay, now I can set those exponents equal to each other. That's a -3. And then I can solve for x. And x comes out -1/7. Let's try another example. Same kind of problem, different example. Change colors. 125 is 5 cubed. Oh, forgot, this problem has a little typo in it. See this 3 right here? Change that into a 2. Otherwise the problem doesn't work out. 25 is 5 squared. So I have the same base. I made both sides have a base of 5. So now I can set the left-hand side exponent, which is 6x plus 3, equal to the right-hand side, which is 4x minus 4. And then I can solve for x. Okay? We actually solved this kind of problem in the last unit, because we did exponential equations in the last unit. And so this is a review of that. Okay. The second kind of equation, if we flip the page, is if they have different bases. And your strategy is this. Step 1, isolate the exponential piece. And then step 2, take the log base 10 or the natural log base e of both sides. So let me show you how that works. So looking at this first problem, 4 to the x equals 15. Well, a 4 and a 15 cannot be made to have the same base. So there's nothing I can do. I'm completely stuck. I can't figure out what that x is. But if I take the log of the left-hand side and I take the log of the right-hand side, this is a new strategy. I've never done this before until now. What that does for me is it allows me to use my rules of logs, which says that this x will come down into the front as a multiplier, and in a sense it's allowing me to get the x down. That's the slang that I use. It's allowing me to get the x down from up high, because now in order to get x by itself, he's multiplying a log 4. So if I divide both sides by log 4, I have my answer. The log of 15 divided by the log of 4. That's what x is equal to. Now there's going to be two kinds of problems, two kinds of directions. One might say leave your answer in exact form. This is called exact form. It means I haven't rounded anything to a decimal. Okay, alternatively, if I do the log of 15 divided by the log of 4 on my calculator, try this on your own right now, log of 15 divided by log of 4, I get 1.95. That would be the decimal answer. Okay, they might say here exact form or exact answer. Or they might tell you round to the nearest hundredths place, round to the nearest thousandths place, round to the nearest tenths place, and then you would actually put that in your calculator and go to decimal. Okay, let's try another one. So example 2, slightly more difficult, because before I do anything, I need to isolate the exponential, which means I have to get rid of this 3. I got to subtract 3 to the other side. That was step 1, isolate the exponential. Step 2, take the log of both sides. So I'm taking the log of the left and the log of the right. And you want to be careful how you write it. You're just writing log in front of the expression because you're taking the log of the expression on the left and the log of the expression on the right. Again, rule of exponent, rule number 3 of logs, says that the x minus 6 comes down in the front as a multiplier. And I'm just trying to figure out what x is. And now it's just a regular algebra problem. In order to get x by itself, right now it's being divided by log 2. It's being multiplied by log 2, so I divide by log 2 on that side. Divide by log 2 on that side. And I'm left with x minus 6 is log 11 over log 2. And then I want x by itself, so I add the 6 over. Okay, that would be the exact answer. And if I type that into my calculator, I would get approximately 9.46. Now, in both of these examples, I took the log base 10 of both sides. And that's what you're going to do on almost every single problem, unless the problem has e's in it. If the problem has e's in it, then you want to be taking the natural log of both sides. Okay. So, now how does this work in real life? Why do I need this skill? So now we're going to do some exponential equation application problems, real life problems. And I wrote you a note up here at the top. What makes these problems different than what we did before today is now we don't know the exponent to use, and we're trying to solve for it. Last unit we did these same problems, but I told you the time, and you were trying to find one of the other variables. Now you're trying to find the exponent, which is usually time. Okay, let's tackle it. Example 1, Bob invested $1,000, that's capital P, in a bank that earns 3%, that means the R is 0.03, compounded annually, that means the N is 1, once a year. How many years, that's T, will it be until his investment doubles? Okay, doubles means it will be worth 2,000. Okay, the formula for compound interest is the one you memorized from last unit. A equals P, parenthesis, 1 plus R over N to the NT. The A is 2,000. The P is 1,000. The R is 0.03. The N is 1, so I'm not going to write it. And the T, I don't know. So I have to solve for T, and I need to do the order of operations. So I need to isolate the exponential, which means this 1,000 right now is being multiplied, so I need to divide by that on both sides. So I have 2 equals, then in the parentheses I have a 1 plus a 0.03. That's 1.03. So here I have an exponential equation. I'm trying to solve for T. My new strategy, my new tool in my toolbox, is to take the log of both sides. Right, why did that help me? Because now the t comes down and is a multiplier into the front. So that will allow me to solve for t. Do the log of 2 divided by the log of 1.03. Typically on these problems, it's actually wanting you to go to a decimal and ask you the time. And I realized I said how many years. I didn't tell you what to round to. So we'll just round to the nearest tenth. 23.4 years. And if you type log of 2 divided by log of 1.03, you'll get 23.4 years. Okay, how about example 2? How long will it take an initial investment of $25,000 to grow to $500,000 at a 9% annual interest compounded monthly? So, my formula one more time is A equals P parenthesis 1 plus R divided by N to the power of N times T. So, divide over the 25,000. 500,000 divided by 25,000 is 20. 1 plus 0.09 divided by 12 is 1.0075 to the 12t power. I'm trying to get t. It's up in the exponent. I have no way of getting that down unless I log the left and log the right. Okay, and then invoking that property of logs, the 12t comes down and is multiplying. Now, I'm trying to get t, and there's two things multiplying the t. So you can divide by the 12 and divide by the log 1.0075. That's just a number. The log of 1.0075 is just a number. I don't know what it is, but my t is being multiplied by it, so I divide by it. I do that on both sides. And that will allow me to figure out t. I'm going to type this into my calculator. Log of 20 divided by 12 times the log of 1.0075 gives me 33.4 years. Okay, again, sorry about not telling you what to round to. Alright, last example. Not a compound interest. I don't want you to think every problem is compound interest. So here's another problem. The value of your boat is decreasing at a rate of 8%. So that means the R is 0.08. If your new boat costs $40,000, that's the initial value, when will it be worth, that's T, when will it be worth 18,000? This is just a general growth formula, or decay formula. Y equals A times B to the X. Y is how much it's worth at the end. A is how much it was worth at the beginning. And now the B is called the decay factor, or the growth factor. And it comes from 1 take away 0.08. And X is my variable of time. So let's make this time here, because I chose T for my variable for when. So 18,000 divided by 40,000 is 0.45. 1 take away 08 is 0.92 to the T. Log both sides. T comes down into the front. divide both sides by the log of 0.92, and that leaves me with t. It says when, so this is time in years, and I get 9.6 years. Oh, I didn't realize there was one more example. One more page. Okay, this example, you don't have to write your own equation. I've seen problems like this before where they give you an equation. They said the growth of a colony of cells can be modeled by this. And you just have to go with it. Okay, trust that they know what they're doing, and they came up with this model. And then t is measured in hours. Okay, how many hours, I'm trying to find t, will it take for the colony starting at 25, that's what the n sub 0 means, it means starting number, to increase to 25,000 cells? How long will that take? So I'm trying to find t. So 25,000 divided by 25 is 1,000. 0.226 t. Trying to get t, it's up in the exponent. The only way I can get it down is to log both sides. The 0.226 t will come down into the front. Log of 1,000, I know you know log of 1,000 is 3, but let's just leave it like that in case it was a number that you didn't know. And then I'm trying to get t by itself. It's being multiplied by 0.226, so I divide both sides by that. It's being multiplied by log 3.1, so I divide both sides by that. So I have the log of 1,000 divided by 0.226 log of 3.1. Make sure when you type it into the calculator, all this is in the numerator, all this is in the denominator. You have it typed in right. It says round to the nearest whole hour. So if I round that, I'm going to get 27 hours. Alright, hope you found this helpful, and I will see you tomorrow.